And now, advisors, shoot.
Is it? Oh, now it's working. Yeah, I had a question to this electricity market study and the vehicle to grid. And so there's two aspects of vehicle to grid. One is the one which I can imagine works much easier, where I sort of control the charging mode by maybe pricing of electricity. But the other one is where essentially the vehicle now provides energy to sort of the grid, right? And do you think this latter one is a economically feasible approach, considering that, you know, the lifetime of each battery is limited, and if I take, I don't know, 100 euros per kilowatt hour battery, and I say it has 2,000 cycles, then it would be 5 cents per kilowatt hour. So the question is, would there be a market where the price I would pay to the owner of the battery would be substantially beyond the 5 cents per kilowatt hour, because otherwise I would just ruin my vehicle without getting any money for it, so to speak?
Yeah, thank you for the question. Actually, we have to point out that an electricity market doesn't mean simply to manage energy. We have a lot of services beyond the energy that has to be properly operated in the grid. That is, we need a reliable grid. That is, I get that it could be acceptable for us to experience a fault from our mobile telephone. You are trying to phone, but you don't have the network that allow you to do that. But it's by far not acceptable for us to have a fault from the electric grid. So there are a lot of services asked to provide reliability and also control of the system that are absolutely interesting also with respect to the economic aspects, because they worth more money, simply. And this means, for example, that your battery could be or should be able to provide a service if necessary. That is, we are not risking a fault each single second, each single day, each single week. Nevertheless, the grid is asked to have tools regulating energy available. So the point is, go on providing your charging services, but you are asked also in case of a critical situation, maybe once a week, I don't know how much probable this could be, and renewables could change the picture, but you could be asked to provide back the energy of your batteries and to release it to the grid. So in the electricity market constant, this is declared as the capacity market. That is not the ampere hour of the battery. Capacity means capacity of your equipment, of your facilities to provide a service. And this could be absolutely feasible. While if you are talking to perform arbitrage, that is to charge the battery when the energy is cheap and to provide back when the energy on the market is more expensive, I absolutely agree with you. Hardly this could be a viable economic model. But once again, we really have many services that are required by the grid, and the point is to evaluate which of those services could be provided by batteries, by mobile batteries maybe, and what could be a technical and feasibility trade-off.
Thank you.
Question to Enrico. So on this, it's exciting to not be constrained by the simplest, most economical shape of the substrates as they have been extruded for 40 years, right? So it's exciting to have that degree of freedom. So I guess a few questions in that regard. One, from the reaction engineering standpoint, what would be the conditions at which we take the most benefit from that? Maybe a few scenarios, because we normally don't think this way because, again, we don't have this degree of freedom. And two, I understand that in the development of these advanced shapes of the substrates, shapes and geometries, you're aided by the additive manufacturing. What's your view on the practical manufacturability of ceramic materials this way, or maybe not ceramic, but what's the glide path to practical manufacturability on those?
Thank you for the questions. Excellent questions, of course. First question: what would we benefit from changing from the conventional honeycomb monoliths to new cellular substrates? Two targets that we have in mind are enhanced mass transfer, which is relevant for many applications at high temperatures, right? So in that case, we know that we can run into mass transfer, external mass transfer limitations primarily, that would limit our abatement efficiency for many different polluting emissions, right? We know definitely from our preliminary investigations that the volumetric mass transfer coefficients in such cellular substrates, like open cell forms, or even better in periodic ordered cellular structures, are one order of magnitude higher, at least, than in the honeycomb monoliths. And this is just due to the change in the flow field, of course. We are going from laminar flow in straight channels to a rather tortuous flow in the path inside the cellular structure. So no doubts that you get a big benefit in terms of mass transfer limited processes. The penalty you have to pay, of course, as you know very well, is pressure drop. So in the end, what we are aiming at is the optimization of the trade-off between mass transfer and pressure drop. And this has very much to do with the selection of the optimal cell geometry, or the optimal cell shape. And this is where we are aiming to. And this is one benefit, okay? Second benefit, however, even more important maybe for some applications, is the heat-up transient. Consider that these cellular structures might have a thermal mass which is much less than the thermal mass of ceramic honeycombs, for example. So the heat up would be much faster for the same conditions. Okay. You would benefit from a more efficient heat transfer for the same reasons related to the mass transfer improvement. And you would benefit from a reduced thermal mass, so a reduced overall heat up time to reach the desired temperatures. Okay. So we are looking at both these aspects. Both of them have very much to do with the fluid dynamics and with the geometry of the cellular structure. Optimization is needed. The nice thing is that we can rely on 3D printing techniques in order to really manufacture the kind of geometries that we are conceiving and which come from our simulation, from our optimization. Okay? And this brings me to the second question. We are perfectly aware that the 3D printing technologies are not yet at the stage where you can really realistically consider them as for industrial production, for industrial manufacturing. But we are in an early stage here. We are still designing and testing the concepts. So we are perfectly happy to have this enabling technology because it puts us in a way in a position where we can really experimentally demonstrate what we have been simulating by CFD, for example. Okay? I'm talking about 3D printing of metals. This is what we do currently. We might come to 3D printing of ceramics. This is not something that we have done yet in our labs, but it's possible, of course, as you know, and it will come also to us. Let me just mention that we are even using 3D printed structures made of resins, plastics, because for some demonstration activities in the lab, they are wonderful. They are extremely cheap, very fast to manufacture, very convenient. You use them for pressure drop measurements, for example, in cold flow experiments. You don't need to go to high temperature, it's fine. And if your resin is resistant to relatively high temperatures, like we have a resin which is resistant up to 270 degrees, we can even coat them and use them in low temperature catalytic experiments, hydrogen oxidation, for example. Hydrogen is very, very reactive. You can go to 100% conversion, or at least to the mass transfer limited conversion at already much lower temperatures than the threshold where the resin would be decomposed. So just for prototyping, for testing, it's wonderful. I'm quite confident, but this is really beyond my knowledge at the moment, I'm quite confident that once we have identified a reasonable geometry for the optimal cell shape, for the optimal structure, then it will be somehow possible to come to an industrial production for that specific geometry.
Okay, thanks. Just a question for Matteo, and the proposal I think is very interesting because it's very, say, put together, like the other projects, very interdisciplinary. They put together different technologies, approaches, and competencies. And in particular, this project is, it's in the framework of what I was citing this morning concerning advanced biofuel, because we start from hydrogen advanced biomass, and also the concept of the e-fuel for the renewable hydrogen, etc. And so there is also an approach in order with the think of minimizing CO2 emission for doing a product that can be done another way.
The microphone.
Oh, sorry. Was just wondering if the evaluation, the optimization of the scheme will also consider the minimization of the CO2 emission. Because in the scheme, okay, we have some steps which are neutral, like, of course, the biomass, starting from the biogas, but still we have the reforming and the methanol production. So it would be interesting if in the technical and economic optimization would be considered also the minimization of GHG emission.
Totally agree, yes, of course. We will do a CO2 balance, or a system CO2 balance, as far as possible on a life cycle basis, and possibly include it in the economic analysis by pricing the emissions of the CO2. So then the idea is also to change the boundary condition, which means also the economics, the cost of the CO2, the price of electricity, and so on, and find optimal design and operations according to these boundary conditions. Yes.
Thanks.
Thank you.
Yeah, I also have a question to you, Matteo. What is the advantage of running a whole process on the intermittence of hydrogen instead of buffering the energy before and then run it on constant flux or power?
The advantage could be in the cost of the hydrogen storage and in the fact that you could do sort of seasonal operation. So as you also mentioned today, you will have probably excess, once the electrification proceeds, you will have excess of, let's say, lower electricity price, let's not say excess of electricity, but lower prices of electricity in some season, for example, summer, and in that case, you may run the electrolyzer on. While in winter, if it is needed elsewhere, so the price increases, you will run the system with the electrolyzer off. And also, so it's a matter of the size of the storage unit that you would need for the hydrogen, and it's that one. And it's also a matter, I think, of safety. So storing hydrogen maybe next to a biomass plant, you don't know what's in the vicinity, might not be a full industrial site, because biogas plants are relatively small, dispersed on the land in the regions. Mm-hmm. So there may be safety issues and economic issue for not doing a storage of hydrogen or a storage of CO2.
Thank you. Maybe a quick question to Marco. So I understand the benefits of using the organic Rankine cycle to recover waste heat and engines provide great opportunity for that high exergy of the exhaust, right? As opposed to, let's say, fuel cells where we struggle with 70, 80 degrees C expelled, exhaust temperatures, much harder to recover those. I did not quite get, so what in your view is the differentiator? What is the differentiator of your project from, let's say, the variety of seed work that had been done in this area? There have been demonstrations and so on. So is the primary emphasis on the miniaturization of the project, so as a target for this specific, for your specific effort?
So in our project, we will mainly focus on EV duty trucks for long-haul transportation. And main differences will be related to the turbine design, because usually small organic rankine cycle systems are based on volumetric expander, which can reach limited efficiency. And so the change of this component will bring a higher efficiency of the system and benefits to the whole vehicle. Mm-hmm. And also the definition of a comprehensive numerical optimization of the system, taking into account constraints on maximum weight of the system and limited volume available on board, will be something that at the moment is not deep investigated in literature.
Thank you.
Okay, I think we can actually thank our speaker and thank also the advisors. Thank you.